The number systems we'll use on the computer are finite number systems. Let's introduce one that's not tied to a particular computer system. In fact, it's kind of a toy example, just to illustrate some of the main points. We'll talk about a 3-digit base 10 number system that uses exponential notation. The number system uses a representation with 4 symbols, A, B, C, and E. A, B, C are the 3 significant digits, each with values from 0 to 9. There's one exception described below. 1 digit for the exponent. E is the number 0 through 9. The value of the number represented by the 4 symbols is notated as n of A, B, C, and E, and it's defined to be A dot BC times 10 to the E minus 4. So this is finite because there's only a finite number of possibilities. There are only 4 symbols, and each symbol is limited to take on 10 different values. It's finite precision because there are a limited number of significant digits. It's called floating point because effectively the decimal point can be moved, giving significant range to the representable numbers. Now there is limited range on the location of the decimal point because E is limited. Here's an example. N of 7356 is 7.35 times 10 to the 6 minus 4, in other words, 735. The range of possible numbers is clearly limited. There's a smallest non-zero positive number, using A and B both equal to 0, C equal to 1, and E equal to 0. And there's a largest number, A, B, and C at 9, and E at 9. Clearly, only a finite set of numbers are represented. There's an additional rule that says certain representations are illegal. A equals 0, E not equal 0 is not allowed. If you have a number like that, simply shift B becomes A, C becomes B, 0 becomes C, and E changes by 1. By not allowing the combination A equals 0 and E not equal to 0, it makes the representation of a representable number unique. For instance, 0.97 times 10 to the minus 2 can be changed to 9.7 times 10 to the minus 3. Similarly, 0.04 times 10 to the third can be shifted to 0.4 times 10 to the second, and finally 4 times 10 to the first. The representations on the left are illegal because they involve A equals 0 and E not equal to 0, while the representations on the right are legal. Let's study this example a little more to see how many representable numbers there are and how they're distributed. Here's a recap of the layout, and here's an abstraction of how the numbers are distributed. Let's go into a little more detail and we'll see what this picture means. Well, there's a total of 9,100 different representable numbers. One number at 0, all the digits set to 0. 99 numbers evenly spaced with a spacing of 10 to the minus 6 from 1 times 10 to the minus 6 to 99 times 10 to the minus 6. This is achieved with A equals 0 and E equals 0 and B and C ranging over their values. There are 900 numbers with the same spacing from 1 times 10 to the minus 4th to 9.99 times 10 to the minus 4th. These occur with A going from 1 to 9, E equals 0, and B and C taking on all their values. The pattern starts to repeat now. There's 900 numbers evenly spaced. The spacing is larger. From 1 times 10 to the minus 3 to 9.99 times 10 to the minus 3. This is the same as before, but now E is equal to 1. E equal to 2 advances it by a factor of 10. E equal to 3 advances it by another factor of 10. 4, 5, 6, 7, 8, and finally the last one, E equal 9. 900 numbers evenly spaced from 100,000 to 9.99 100,000, or in other words, 999,000. Once E was large enough, a regular pattern emerged. An identical number of numbers evenly spaced in a range. The ranges are non-overlapping. Where one range leaves off, the next range begins. Each range is 10 times the previous range, and the spacing is also growing by 10. That's what this picture is trying to depict. Within certain intervals, the spacing between numbers is equal. Larger intervals have larger spacings. Smaller intervals have smaller spacings. And there's no overlap across these intervals. Another thing to notice is that the spacing doesn't change across these three groups, really two groups and a single number. All of these numbers are spaced 1 times 10 to the minus 6 from one another. Moreover, there's more numbers in this group of numbers that have this minimum spacing than there are in the groups of numbers at any other spacing level. Let's close with a few more observations about this finite number system. There's a recap of how it works, an example to illustrate how it's used, and let's be aware of what it can't represent. For instance, 5,632 is not a representable number. It's not that it's too large, it just isn't representable. The closest representable number is 5,630. What are some issues? Well, there is a largest representable number, as well as a smallest non-zero representable number. So this finite number system has a limited range. Adding two representable numbers may not result in a representable number. Of course, it may become too large, but it also just might become not representable. For instance, 5,510 is representable, 122 is representable, but we already know that the exact sum, 5,632, is not representable. More generally, just arithmetic on these representable numbers may not result in a representable number. Consequently, we'll have to require of the machine, the computer, that any basic operation, plus, minus, times, and divide, will always yield the representable number that is closest to the exact answer. We'll mention a little bit about how this is done later on, but that's certainly a requirement that you would want. Accepting the fact that your finite number system has gaps in it, but still requiring that operations whose exact behavior produces non-representable numbers on the machine should at least produce the closest representable number. In this sense, we'll need some notion of rounding to the nearest representable number.